So what we'll start with today is we're going to prove properties of logarithms by graphing. We're going to start with the first example. We'll give an equation y equals log base 2 of x plus c. And some people would say, oh, you can use the distributive property here. And you can say, hey, let's multiply both the x and the c by log base 2. And then you can rewrite it as y equals log base 2 of x plus log base 2 of c. That's what the distributive property says you can do. And that's what we're going to take a look at right now. We're going to take a look at these two different equations here. One of them before the distribution and one of them after. But we're just going to pick a value for c right now. I've got 1, 2, 4, 8, and 16. I want somebody to pick a number for c, one of those numbers, anyone you want.
4.
4. 4 is done. So we're going to pick 4. All right. So what we can do then is we can write the first one as log base 2 of x plus 4. Y equals. And then we'll write the second one as y equals log base 2 of x plus log base 2 of 4. All right, so that's just because we picked the value for c there. Now on this first equation, if I were to solve for it, I would go ahead and say, let's change the form. So 2 to the y equals x plus 4. And then I would subtract 4 from both sides and get 2 to the y minus 4 equals x. And now I can plug in values for y and solve for x. We're kind of working late on both sides here. Or working from the y side back to the x side. So let's just use the same exact y values we did in the warm-up. We'll just go -2 to +4. And if I did -2 here, I get 1/4 minus 4. And I can rewrite 4 as 16/4. And then 1 minus 16 is -15. So my first x value is -15/4. And then we try the next one, 2 to the -1 minus 4. That one's going to be 1/2 minus 4, so that'll be another one that deals with a fraction, unfortunately. 1/2 and 4 can be rewritten as 8/2. Remember, I'm just rewriting it as 8/2 because you can say 8 divided by 2 equals 4. And the same thing with 16/4, I can rewrite 16 divided by 4 is 4. So I'm just changing 4 into a number. You can get it by multiplying both the numerator and denominator by 4. So let's say 4 times 4 is 16, and then put it over 4. And same thing with this one down here. I can do 4 times 2 is 8, and then put it over 2. And that gives me the common denominator. Now I can do 1/2 minus 8/2, and I get -7/2 equals x. And once I have -7/2, now I can go ahead and say 2 to the 0 power minus 4. The rest of them will be a lot easier. 2 to the 0 is 1. 1 minus 4 is -3. And then if I do 2 to the first power, oops, minus 4, I get 2 minus 4, which is negative 2. 2 squared minus 4, that's going to get me 4 minus 4. That's going to get me 0. And then 2 to the third is 8. 8 minus 4 is 4. 2 to the fourth is 16. 16 minus 4 is 12. We'll do those last couple a little bit faster. But that's what we end up with on the left side here for this y equals log base 2 of x plus 4. I'm not going to graph it just yet, but we'll move to the right side. First, we have log base 2 of x, which is fine. The second part we have is this log base 2 of 4. I don't want to deal with that. I can't really do anything with these two separate logarithms. So what I can do instead is I can say, well, log base 2 of 4, that equals an exponent, a question mark. So if I rewrite it in a different form, 2 to the question mark equals 4. What does the question mark have to equal to get 4? If I do 2 to what power equals 4?
Wait, so are you taking the 4 out of the second logarithm and just putting it on the other side of the equal sign? Or is it still in the question mark?
Oh yeah, so what I'm doing is, so I have this right here, yes? This log base 2 of 4, and I'm saying, okay, well, logarithms solve for exponents. So I'm just changing the form and saying, hey, what's the exponent? Can we figure out what the exponent is? Because if we can, and it turns out we can, because 2 squared is 4, that means log base 2 of 4 is 2. And because that's a true statement, I can do a substitution now and say, hey, it's going to be a lot easier to work with this equation if I have log base 2 of x plus 2 instead of two different logarithms. Does that make a little more sense?
Yes.
Okay, so that's the idea for the second part. It's going to be easier to deal with the equation if I can get rid of that log base 2 of 4. And I can, which is nice. It doesn't always work, but it works in this situation. Now, if I subtract 2 from both sides, I get y minus 2 equals log base 2 of x. Then I can change forms and get 2 to the y minus 2 power equals x. Now, I can use those same y values that I used on the other side, and I can plug in and solve for x. And hopefully I get the exact same x outputs. And that'll prove that these two equations are indeed equal, that this distributive property works. So first one, I get 2 to the negative fourth. 2 to the negative fourth is like 1/2 to the positive fourth. You can take a negative exponent and flip it upside down, make it a positive exponent. And then 1 to the fourth is 1, 2 to the fourth is 16. So I get 1/16 for the first one. And then I can do the next one. I'll do -1, and I get 2 to the negative 3 power. It's 1/2 cubed, which is 1/8. And already I know I'm off to a bad start because I know on the other side I had negative numbers. And I'm not getting those negative numbers here. 2 to the 0 minus 2. That's going to be 2 to the negative 2 power. 1/2 squared, that's 1/4. And then we get 1/2, we get 1, we get 2, and we get 4. So that ends up being the rest of our values if we worked through all of them algebraically. But the thing we set out to prove was, are these graphs the same? I've got the same y values, but then this time I have completely different x values. So without even graphing it, I can answer the question at the bottom here. It says, no, they're not the same. So that answers that question. Are these two graphs the same? No, they are not. Okay, so again, without even graphing them, and honestly, I don't see the point in graphing them at this point. We've seen the table of values. We could graph them really quickly on Desmos if we want and prove they're definitely not the same. And speaking of Desmos, let me show you real quick. We're going to pause here. Okay, so now let's take a look at another example here. It says below we have the parent function of log base 2 of x. So we talked about parent functions a little bit on Tuesday. Just whenever you have just something by itself, it's just the regular base and just the x. And then we have a function over here, part B, that says log base 2 of 4x. So the first thing I want to do is take this parent function A, and we're going to label as many x and y values as we can. So for example, I see one right there at 1, 0. I see another one right there at 2, 1. I see one right there at 4, 2. Okay. I see one here at 8, 3. And I finally, last one, I see one here at 16, 4. So that's just a bunch of x and y values from this graph, y equals log base 2 of x. And I'm going to even go one step further and rewrite my xy table down here. So I had 1, 0, 2, 1, 4, 2, 8, 3, 16, 4. I pulled all of these points from the graph. Now I want you guys to do the exact same thing on graph B here, right next to it, which is, this is not the parent function. This one's log base 2 of 4x. So see if you can find some x and y values and then create a table of values for those x and y's. Okay, so take a second and do that. Okay, so what's one point we found on this second graph? One point that we can see is clearly integer values.
8, 5.
8, 5. There we go. There's one. What else? 1, 2 I got. All right, someone else, different point. 2, 3. Good. All right. 4, 4. Okay. And one more. I got 16, 6. So now let's go ahead and write those ones down. 1, 2, 2, 3, 4, 4, 8, 5, 16, 6. So I wrote it down as a table because I think it's going to be easier to see from the table of values. But notice that in both of our graphs, x columns 1, 2, 4, 8, 16, exact same x values. But the y values are different. Look at the y values here, 0, 1, 2, 3, 4. Over here, 2, 3, 4, 5, 6. So what's different about the y values in B?
They added 2.
They added 2. Other than that, the graph looks exactly the same, but all the y values have added 2. So think about, you take a logarithmic function and you want to translate it up 2 units. How do you do that? What do you do to the original equation A to change it 2 units up?
You put plus 2 in front of the equation.
Yeah, in front of it or at the end of it, like that. Exactly. So what we can do is we can say, here's an equivalent equation. Y equals 2 plus log base 2 of x. Or you could write it as y equals log base 2 of x plus 2. You can write it either way. That addition's interchangeable. You just want to be clear that the x or the 2 is not in parentheses. It's not part of the logarithm itself. But that is an equivalent equation of writing this translation here. So what we can also say is that it turns out log base 2 of 4x is equal to 2 plus log base 2 of x. Those two equations are equal, just like what we did on the warm-up where we saw 2 different equations that turned out to be equal. All right. Now, what I want you guys to do, use the same parent function from example A, and then go through these four graphs and write an equivalent equation for each of the four. Thinking about translations, vertical translations, moving the function up or down only. So take a few minutes to work on these four equations, create an XY table, and then see if you can tell whether it's moving up or down. I went ahead and did problems 1 and 2 in terms of finding the points and getting the tables going, and we're comparing them to the values from A above. So again, we see the same x values, but this time the y values are 3 units higher. So this first one should be y equals 3 plus log base 2 of x. Or you could say y equals log base 2 of x plus 3. It's perfectly fine whichever way you write it. All right, just as long as you understand that the 3 is not part of the logarithm. What about problem number 2? What do we get for that one? What should we get for an equivalent equation?
Y equals 4 plus log base 2x.
Exactly. So this one is going to be 4 plus log base 2 of x. All right, or you could say log base 2 of x plus 4. And again, the x values are the same, but the y values have increased by a factor of 4. They've all added 4. So that's showing a vertical translation up 4 units. Now, when we do number 3 here, what happens, it looks a little different. This time, the points are moving down. So it's 1 comma negative 3, 2 comma negative 2, 4 comma negative 1, 8 comma 0, and 16 comma 1. So this time they're moving down 3 units. So what do you think we would say? Log base 2 of x minus 3, or 3 minus log base 2 of x. Okay. And then the last one here is going to be y equals, oops, sorry, I wrote this one wrong. It should not be 3 minus log base 2 of x. It should be negative 3 plus log base 2 of x. My apologies there, because it should be a minus 3. So this one might be easier to write as just the log base 2 of x minus 3 to keep it simple. The last one should be log base 2 of x minus 4. Notice that there's a common factor of 16 here. One of them was plus 4, one of them is going to be minus 4. And then same thing over here. We had an 8 and an over 8, and that depends on what, that changes the sign from plus 3 to minus 3. All right, so we see that same thing happening there. Okay, so that's the idea with these graphs, that there are equivalent equations out there. So for example, we already said log base 2 of x, or log base 2 of 4x, we did this one up above. That's the same as log base 2 of x plus 2. Well, one thing we want to talk about here is the 2. We could technically rewrite it as, what is it? Log, what's the best way to say this? We can write the 2 as log base 2 of question mark equals 2, right? We know that there was some type of way to turn that 2 back into a logarithm. And if we rewrite this, as 2 to the 2 squared equals question mark, then we know 2 squared equals 4. So it's safe to say that log base 2 of 4 equals 2. And then that means you could write this as log base 2 of x plus log base 2 of 4. All right, so that's kind of what's happening here. So we're saying log base 2 of x plus log base 2 of 4, that's the same as log base 2 of 4x. kind of a weird way to look at it there, right? It's because I'm taking something that's simple and I'm making it a little bit more complicated by putting this log base 2 4 back into place. But hopefully what we're seeing is hey, two separate logarithms here can be rewritten as a single logarithm, in this case log base 2 of 4x. I'll show the next one in a different way. Technically we can rewrite log base 2 of y of 8x, as log base 2 of x plus log base 2 of 8. Or let's say log base 2 of 8 plus log base 2 of x. That's a legal move we're allowed to do. We're allowed to write it like that. But I want to clarify that log base 2 of 8, we could rewrite that in exponential form and figure out what the exponent is. 2 to the question mark equals 8. And it turns out to be 2 to the third power. So what that means also is we can say log base 2 of, well, if we replace log base 2 of 8 with 3, we can say 3 plus log base 2 of x. And that's what we had up above for this equation up here. 3 plus log base 2 of x. So we can say log base 2 of 8x is the same as 3 plus log base 2 of x. But I wanted to make sure that we note this middle step here. Log base 2 of 8 plus log base 2 of x. If we do the next one, we can say log base 2 of x plus log base 2 of 16. Notice that I'm just doing the addition interchangeably. That's perfectly fine. You can always interchange addition. And this brings up the point that log base 2 of 16 equals 4. So we could write this one as log base 2 of x plus 4. And that's what we had up here. Log base 2 of x plus 4. As an equivalent equation to log base 2 of 16x. So this will keep happening every problem we work through. The next one, a little different because now it's x divided by 8. This time we're going to write it as log base 2 of x minus log base 2 of 8. So it was division of two numbers, but this time we'll write it as subtraction. And we'll say log base 2 of 8, we already said is 3. So this one we can write as log base 2 of x minus 3. And that's what we had written up here for an equivalent equation for log base 2 of x over 8. And then the last one here, log base 2 of x minus log base 2 of 16. And we say log base 2 of 16 equals 4. So we can write this as log base 2 of x minus 4. So the whole purpose of today, using the graphing, was to recognize, hey, we know how to do translations, and we can see there's a vertical shift going on in these logarithmic functions. So we can write an equivalent equation. And the purpose of those equivalent equations is because we have properties of logarithms that we want to prove. And this is helping us prove that there are two things. There's one called the product property, which says if we have two numbers, like for example 4 and x are two different numbers, or 8 and x, we can rewrite it as two separate logarithms that are being added together. So in general, we can say log base b of m plus log base b of n. We can write that as two separate logarithms that are being added together. And then the weird part is that we simplified some of these logarithms, like because 3 became log base 2 of 8 became a 3. The same thing happens with the quotient property. If we have two numbers being divided, we can technically say, hey, we have two logarithms. where the second one's being subtracted from the first. All right, and that's another property of logarithms. That's how these properties work. That's important because on our assignment tonight, we're going to start practicing these properties of logarithms. And that's what problems 5 through 10 will ask you to do. So like problem 5, for example, says expand each logarithmic function into an equivalent expression. So because we have two numbers being multiplied, we could technically write this as log base 5 of 5 plus log base 5 of x. We can write it as two separate logarithms being added together. But then the first part of it, the log base 5 of 5, we might be able to recognize, hey, I can say that's 5 to the question mark equals 5. So that's going to be the first power. 5 to the first equals 5. So log base 5 of 5, therefore, equals 1. So we can write this as 1 plus log base 5 of x. And that's what our final expanded expression would be. That's how I'm going to expect you to do problems 5 through 10 on the assignment. So we already did problem 5 there, just together as a group right now. All right, problems 11 through 13, I'm just asking you to rewrite each logarithmic function in exponential form. And problems 1 through 4, I'm going to ask you to write an equivalent equation for the given function. I expect you to use the parent function y equals log base 3 of x as your baseline. So you might want to graph that one in Desmos, write down the xy table for log base 3 of x, and then compare that table to problem number 1. And then for problem number 2, it's log base 4 of 16x, so you're going to want to use log base 4 of x as the parent function. Okay? So that's the idea for problems 1, 2, 3, and 4. Problem 3, you'll want to use log base 2 as the parent function. Problem 4, you want to use log base 3 as the parent function. Okay? So that's the idea for problems 1 through 4 there. And then 5 through 10, I already explained it. 11 through 13, I already explained it. That's the idea for your homework assignment.